Okay, ultimately, the kinds of problems we're going to solve, I think of them as engineering problems. This isn't limited to engineering, but these are the kinds of real problems that real engineers solve. Let's say that you're designing a winch for a moving company. So there's a truck, and inside the truck, there's a winch with a rope wrapped around it, and that winch is designed to pull things up a ramp. So if you have something really heavy, like a big old, like a piano on wheels, then you tie the rope around the piano and you switch on the winch and it can pull that piano right up into the truck. Now here's the problem with that. And again, these are real problems that real engineers solve. If you turn it on and it's like moves at 1 inch per hour, then that's a problem. It's not moving fast enough. It's got to go faster. But if you turn this thing, like you crank this thing all the way up, and it tries to move that piano up the ramp in like 2 seconds, the rope is going to break. The rate at which it moves the piano up the ramp determines how strong that rope has to be. So a real engineer might ask a question like, well, what is the maximum force that this winch can possibly exert on the rope before the rope is going to be in danger of breaking? Or how quickly, what's the minimum amount of time that we could take something from rest and pull it up the ramp without the rope breaking? Or what's the best angle of the ramp? Like if what's at a certain point, if that angle is too steep, then you're going to have a bunch of broken ropes, right? And this is, again, like, these are real problems. And those of you who have done things like been on ski lifts or gondolas, like, like this is life and death in some cases. Most of the time, these kinds of things are not necessarily life and death, but I mean, human beings move a lot of stuff around the world. So we've got like big cranes loading and unloading ships and trains and trucks, and this is real life stuff, and this is the kind of thing they have to know. I mean, probably you're like me, and you've looked at something and you've thought, well, I hope that holds. I mean, am I the only one who's had that thought before? Right? Like you look up at something and you realize, like, boy, if that breaks now, I'm in trouble. I think about that literally every time I walk under these breezeways, which are like, I don't know, I don't trust them. We've done some earthquake reinforcement, but I've seen what's up there, and those were not designed. Like, if there's ever an earthquake, get out from under the breezeway. Do not stand in those breezeways. That stuff is coming down. And those are the kinds of things that like an engineer would think of, and it would have been nice if when they built the school, engineers would have thought of that, but they didn't. So what do we have to do to solve a problem like this? Well, ultimately, it all involves the rope, where it's attached to this object, piano, whatever it is. What kinds of things determine the force in the rope? Well, one thing is the amount of time that it takes, because if it happens really quickly, that means that it's going to have to have a very large acceleration. We know something about acceleration. We know that if we have constant acceleration, we're going to see velocity that's increasing linearly and position that's increasing exponentially. It's going to be a parabolic curve. So there's our motion graphs. We care about this stuff because this stuff is going to be what allows us to relate the amount of time that goes by to the force in the rope. What about the other things that determine it? Well, part of it is going to depend on like how heavy this thing is. Like we all know that. Like this, whatever it is, it's got some weight to it. And gravity is pulling this thing straight down toward the ground, except the ramp is in the way. So gravity's not, like if we were to just let go, it's not going to go down. I mean, I guess the ramp could collapse, but if the ramp doesn't collapse, it's going to roll down the ramp. So that means there's like some part of the force of gravity is what's causing the piano to tend to want to go down the ramp. And then we've got the rope itself that's pulling, and then you all know friction is a thing, and we haven't talked about the details, but friction is always going to be opposite an object's motion. So we need to be able to think about acceleration and constant acceleration, how that relates to our kinematic variables. So there's motion graphs, there's one-dimensional motion, there's kinematics, there's uniform acceleration, all those skills. And then we have to think about another set of skills, which is how do you deal with the fact that, like in this case, gravity is pulling one direction, friction is pulling in one direction, the rope is pulling in another direction, and that's not even all the forces that are acting on this. There's other things that are pushing or pulling on this. We have to be able to deal with forces that aren't all in a straight line, because we have to be able to deal with motion that's not all in a straight line. So the skill that we're going to start with today is looking at this two-dimensional motion stuff, and that's not what I want to actually look at. And we'll look at the first part of this today, and we'll continue looking at this next week. So, so here's the skill. We've got to be able to evaluate the motion of objects that are moving not just in a line, but are moving on a plane. And this is a conceptual thing. When I show you some things today, it's going to seem relatively straightforward, but it's not. It's one of the more complicated things that we're doing. And then there's a kind of a mechanical piece too, which is, okay, well, if we have things that are moving in more than one direction at the same time, then how do we deal with that? And the answer is that we are going to think about their motion as being in two different directions at the same time. So an object that's moving this way, for example, up and to the right, we may think of that as moving to the right and moving up at the same time. To do that, we're going to have to do some math, vector math. And you've done some of this before, but we're going to use it a lot. And then sometimes we're going to take pieces of motion, like it's moving this way, and we're going to put those back together and say, so overall, it's moving this way in this direction. When we think about two-dimensional motion, we're going to start by talking about projectile motion, because projectile motion is generally the easiest to understand. There's an inherent predictability to it that happens because we've been dealing with projectile motion all our lives. Projectile motion is the reason that when you throw a ball, somebody else can catch it, or when something is coming toward you, you can dodge it and get out of the way. You know that it's going to hit you if you're in a certain spot. We have an intuitive ability to do those computations in our brain, because for all of our lives we've been dealing with projectiles, things that are in the air moving. Projectile motion is not the only type of 2D motion though. So anytime an object is moving, not just along a line, we consider it to be two-dimensional motion. You'll see an example in just a minute of a perfectly horizontal plane, something rolling on the floor, experiencing motion in one dimension and then in a different dimension at the same time. We can think about like a pool table. We can think about objects on a slanted surface. When we think about the cart rolling down this ramp, that cart is moving in one dimension. If we think about the ramp itself as being one dimension, but what if we were to drop something onto the ramp and then have it roll down from there? Now we have two-dimensional motion, and that two-dimensional motion involves like a weird axis. It's not projectile anymore. So we have to think about some of these things differently. And the key piece here is that if we define a plane by using two intersecting axes and the angle of intersection is 90 degrees, then there is a magic physics thing that happens. And that magic physics thing is that motion along one of the dimensions is completely independent of the motion along the other one. What that means is, if we know enough about an object's motion, for example, left to right, then we can make predictions about how far it's going to go, even if it's also moving up and down, and vice versa. If we know enough about an object's up and down motion, we can figure out where it's going to be vertically, how fast it's going to be going, how long it's going to take to move between two positions, even if it's also moving left to right. So this example here, this drawing is kind of evocative of maybe somebody kicking a soccer ball. So if there's a soccer ball on the ground and somebody kicks it, then it's going to go up in the air and it's going to come back down to the ground. And what I want you to imagine when you think about two-dimensional motion is imagine that as this person kicks the soccer ball, there's a drone up above the field, kind of high enough up that you can't really, like it's like, 100 feet in the air. So it can see the soccer ball, but there's not much relief. It can't tell how far the soccer ball is off the ground. And in that case, the drone is really going to be unable to tell the difference between a soccer ball that's kicked up into the air and comes back down, and another soccer ball that's just kicked along the ground so it rolls at the same speed. In fact, if there were two soccer balls right next to each other, one was kicked flat, one was kicked up, but they were kicked in such a way that they had the same horizontal speed, then what the drone would show is two soccer balls that appeared to be moving side by side until they converged on the same point. You wouldn't know that one of them was coming up and then going back down, and one of them was just staying on the ground. The other way to think about this kind of motion is if you were, instead of above the soccer ball, you were behind the kicker. So if I'm kicking a soccer ball, kaboom, you're standing right behind me. Now imagine what would happen if I kicked a soccer ball straight up in the air while somebody else right next to me kicked a soccer ball so that it went up in the air and came down some distance away. And again, like if you're right there, you can kind of see it, right? Like I can tell when things are moving away from me. But the farther back I get, the harder it is. If I'm 50 feet away and I watched two people kick a soccer ball and I saw them both go up in the air and they both came back down, I don't know that I'd be able to tell which one landed further away. One of them might just go straight up and come straight back down. The other might go straight up and then come back down some distance away from the kicker. If you were to watch them from behind the kicker at some distance, what you'd see is both balls come up, they're both at the highest point at the same time, then they both come down and they both hit the ground at the same time. We don't need to know that one of them is moving horizontally as well. Just like in the first example, we didn't need to know that one of the balls was moving vertically. All we need to do is know how they're moving left to right. That is called independence. And that is one of the really fundamental pieces of physics, that if we are looking at motion or other types of things, any quantity that could be measured in a direction, if we take our directions and we think of one set of directions as occurring along a line and another set of directions as occurring along a line that's perpendicular for that, to that, then we can separate all the information. We can consider each of those axes completely separately, and all the physics will work just as if it didn't have any motion in the other axis. So that's what we're going to be doing. We're going to analyze these separately using kinematics equations and a bunch of other equations. We're going to think about forces, we're going to think about momentum, and we're going to think about all of those things in two, and not in this class, but theoretically we could think about three-dimensional motion as well, right? So like a curved ball is moving through 3 dimensions at the same time. It's going up and down, it's going toward somebody, and it's also going left to right with respect to the person who's throwing it. So there's a lot of stuff that can go on with motion. All of it can be thought of as completely independent on axes that are at 90-degree angles to each other. We are going to talk a little bit today about vectors. You're going to do some work with vectors, but mostly when we start thinking about vectors, that'll be next week. Vector quantities, we've already looked at them. I mentioned it a few weeks ago, but I didn't emphasize it. I'm going to emphasize it now. Vector quantities tell you how much a quantity is and also in what direction. Some things we don't care about. Like if I want to know about energy, for example, I don't care about direction. If I run around a track 20 times, I'm going to be really tired. If I run in a straight line for the exact same distance, I'm also going to be really tired. I use the same amount of energy. whether I'm like moving a long distance away from where I started or whether I just move a bunch and end up in the same spot. But other times, we do care. If I offer you every single penny that's in my wallet right now, and some of you are like, well, Brie, you're a teacher, you've got nothing. Well, 2, 3, 4, it's full of money. This wallet is full of money. And I will give all of it to anyone who can throw this rubber ball into this wastebasket. And the only trick is you have to throw the ball in that direction. Right? It's like direction matters. Yeah, Adam, nice try. Right? Like it direction matters. And you could get tricky, you could do it like a bounce shot or whatever, but the reality is that in physics, we're often thinking about like, how do we make two things converge, right? Like if you're a police officer and you're trying to pull somebody over and they drive past you, you don't like start speeding in the opposite direction. Like you could go really fast, you're not gonna catch them. Direction matters most of the time in physics. So when we think about quantities where their direction influences the results, those quantities are called vector quantities, and we're going to have to deal with those. We're going to deal with a bunch of different two-dimensional things. Wait, hang on. I want to go back because I want to watch. I'm going to have you guys watch some videos that demonstrate this, these are short. And they're super informative because they accomplish a visual of what's going on that I simply can't do in words or in drawings. Okay, so let's start with this one. So this is kind of a classic demonstration of what happens when two objects are in free fall. They both start with no motion at all vertically. One of them has some horizontal motion to begin with. So if you, this is in slow motion, so it'll take a little bit, but he's got this little apparatus, he's got two balls, one of them is going to be hit sideways, one of them is going to be dropped, and you can see they both hit the ground at the same time, and they're even bouncing at roughly the same time. It's not perfect, but like they're in basically the same point, vertically at the same time, but one of them is also moving left to right at the same time. And we're going to take advantage of that. That's one of the key features of projectile motion, is that if something has a certain distance to fall, it will take the same amount of time to fall that distance regardless of whether it's moving horizontally or not. Another example, and I love this one because I swear these are the exact same floor tiles that we have, but I did not take this video. I really think these are exactly the same, like right down to the like
generic school.
Yeah, these are like, yeah, so this is, but I didn't make this. I don't think Mr. Kirsch did either. So in this one, we're gonna see this a couple of times. So we've got a ball that's moving left to right, and then it's tapped by the ruler, and then it starts moving at an angle. When we watch just the left to right motion over time, what we see is that for each frame, which is probably about a 30th of a second, it seems to be moving about the same distance. This is constant velocity in this direction. When it's tapped with the ruler, it's tapped in such a way that it doesn't change that horizontal velocity. So if we look at what happens next, it continues to move about the same distance horizontally with each frame, but now it's also moving what looks like vertically. Now this obviously is not true vertical motion. This is a top view of motion. So we're not looking at free fall there. We're looking at an object that has no acceleration for the second part of the video as it moves both left to right and up and down. Yeah.
What about that little gap?
The little gap is just an artifact from where they tap it and they just didn't have they didn't put the line in. So this is showing 2 frames. So the rate is the same, it's just we're dividing by twice the amount of time, so it went twice the distance. All right, this next one is, so this one is great, and I'm gonna turn on the volume for this because this guy is fun to listen to. And this is old school stuff. This is what my physics classes were like, both in high school and in college. We don't do this anymore because this kind of stuff requires equipment that is designed for one demonstration and one demonstration only. And back in the day, like, schools had a lot of money. And so a teacher would be like, I want the demo. I want the cart demo thingy. And people would be like, okay, here's $1,500, go buy it. And then we'd use it like once a year. But those were the good old days. Now, we take videos of people using equipment that's 50 years old. But this was what my physics experience was like, because all this stuff existed back then.
So here's the golf ball. I'm going to fire the gun now. Close.
Nice catch.
Close. Reasonably close. Well, since it's only reasonably close, perhaps...
Hold on just a second. I think we need to go back here.
No way. No way.
Not the way they got back.
I don't know, man.
He's a time traveler.
That's pretty good.
He's wearing the same color shirt too.
It's ridiculous. I had slightly shorter hair back then. That was like a couple weeks ago.
So this was a sneak demonstration. Obviously, like, the point of this is not really to show you anything about motion. This was all about time travel.
He's wearing the same color.
That is...
Well, I mean, you said it, and then I had to go back and actually see it for myself.
I know.
And then I kind of changed history. So.
He's a nice guy, that professor,
Yeah,
isn't
we
he?
found your ancestor back.
Yeah.
Perhaps it would help if we give it a little bit of leeway. There goes the gun. Here comes the ball. And this is just in case.
This is what my college professor sounded like too. He was Eastern European, and it was just a great class.
Take it down. So as I'm going to push this now, give it a push. The gun will be triggered when the middle of the car is here. You see how high that ball goes, so that ball will go. And depending upon how hard I push it, they may meet here, or they may meet there. You ready for this?
It's going to catch
You ready? I'm ready. Physics works.
So
Physics works.
the point there was the ball had some horizontal motion. When it was shot, that horizontal motion didn't change. It gained some additional vertical motion. It went up and it came back down. But it went up and came back down in such a way that it was still moving left to right at the same rate that it had been originally. Okay, and then this last one, the caveat here is, while these are really cool demos, I'm not showing you this to encourage you to do something like this. This is not the most reckless thing you'll ever see. It's also not safe at all. So please don't do this, don't do stuff like this. These were college students. I don't know what the context of this activity, this assignment was. We've got the videos to use, but don't you go doing stuff like this, please. So, no. So this is, what we're looking at here is a truck, and it's the equivalent of what we just saw, but there's a little bit of nuance here that's kind of fun to think about that's actually relevant to the work we're going to be doing. So this is just throwing a ball up in the air, and you can see that the ball basically does not change its position relative to the person throwing it. It appears from that position's point of view that it just goes up and comes back down. If we look at the overall path of the ball, there's our parabolic arc, okay? And this is not a position versus time motion. We're looking at X versus Y position. It's also parabolic in this case. But now if we think about just the ball as it moves up, and then we're gonna stop here, look, it goes up, and then it comes back down. If you ignore the stuff in the background, that ball moves just the way you would expect if he hadn't been moving it all and just threw it up in the air. Okay? And it happens the same way, even if he moves a little faster, although you can see that this time, he has to lean a little bit. He has to lean a little bit to his left. It goes up, and it's kind of losing ground a little bit, right? So there is some degree to which this thing is losing speed as it moves horizontally, okay? And we can see that here, so it goes up, and now it looks like when we keep this reference frame steady relative to the thrower, it kind of looks like it moved a little bit to his left, to our right. Okay, so now let's try it with a tennis ball. Tennis ball goes up, tennis ball comes down, and in slow motion we can see it goes up, it's right above his hand, but it's kind of shifting its position, and he has to shift to be able to catch it. And it's not until the truck speed is increased to about 25 miles an hour that things break down. So now we have an example of something that is no longer exhibiting true projectile motion. And the reason, as most of you can guess, is air resistance. If this were in a vacuum, it would have worked as expected. But in real air, this ball is moving to our left fast enough that the air is kind of slowing it down. So, and that's something we may need to take into consideration. The projectiles that we're using, are pretty light. They're also pretty aerodynamic, but they're not very heavy. And it turns out that their small weight, their small mass means that they are going to experience some air resistance. The faster they're going, the more likely it is that we'll see it. So that's going to be something you may need to factor in to the work that we're going to be doing on Thursday. Here is, so in general, when we're working with two-dimensional motion, which includes projectile motion but is not limited to projectile motion, here's a few things we're going to need to consider. One is we now have two sets of variables to keep track of, one for each axis. The other is what we know about a particular scenario is not always the same. We're going to start with the simplest case. We're going to start with a projectile launch where we know how far up above the ground the launcher is, so we know how far it has to fall. We know the angle of launch, and we know the speed of the launcher. We don't always know those three things. There's lots of predictions we can make if we know other things besides those three things, but if we start with those three, we get what's kind of the classic projectile motion problem, and that is to figure out how far will an object go if it is launched from a projectile launcher. We could launch it horizontally, or we could launch it in an angle. We're going to start by just thinking about a perfectly horizontal launch, okay? And we're going to make some assumptions that are not accurate, okay? One is that we're going to assume that it's in free fall, which means that there is no acceleration as it moves left to right or right to left, and its acceleration down toward the ground is exactly 9.8 meters per second squared. That's simply not going to be true in real life. It's never going to be faster than 9.8 because nothing is ever going to be pulling it down in free fall harder, but it will often be less than 9.8 because of air resistance. And our horizontal acceleration is typically going to be some amount of acceleration in the opposite direction of the object's motion. Yeah?
That equation, that negative 9.8 meters per second squared, that's specifically Earth's gravity?
Correct, yeah. We would have a different value if this were on a different planet. Yeah. Yeah. And which obviously is not something most of us are going to have to deal with, but it is something that people have had to deal with, right? We've had people on the moon where this number is much smaller. And then if we know how fast something is moving, we know how far off the ground it is, and we know what the launch angle is, then we can figure out a bunch of stuff. On Thursday, you're gonna do this. You're gonna do it with the projectile launchers that you used, which means you're gonna know the velocity, because you used tracker to figure out how fast those things are coming off the launcher. And I'm gonna point out there, I'm gonna stop for just a second and point something out that most of you discovered, but I wasn't able to verify this with everybody, so I want to make sure that you hear this from me and that you then look at your own data or the data that you got from the launch that I posted on Canvas. And what I want you to think about is how fast was that ball coming off of the launcher when you launched it horizontally versus at an angle. And the example that I gave you was a 20-degree angle, but you might have launched it at a different angle. And if you launched it at a, when you launched it at a horizontal angle, then you would have put your axis on like this, and what you should have been able to do was to create a series of points in tracker. Tracker would have generated a parabolic curve for those points and told you that y equals ax squared plus bx plus c. This is the initial speed of the launcher in this direction, okay? And although this, yeah, this would have been x, sorry, hang on, let me do this again so that it's really clear. This would have been x equals at squared plus bt plus c. Sorry, I need to be more clear about this. So for the horizontal part of this motion, the left to right part of this motion, this was our initial velocity. If you were looking at your angled launch, then you would have had to take these same axes and turn them so that it was in the direction of the launch. And now we don't have a horizontal and a vertical anymore, but you can still use tracker to make a curve, and in this dimension, which for most of you would have been the x dimension, you can still have it come up with a quadratic equation to match it, and it would have been at squared plus bt plus c. And this would have been different, and this would have been different, but this should have been about the same. And it's not the horizontal velocity, because it's not moving horizontally, it's the velocity in this direction. And it even said that in the assignment. It said, what is the ball's velocity in the direction of the launch? Which is kind of a weird question to ask, but what I'm asking is, how fast was it moving along this line? And if we tilt our coordinate reference axes and then do a curve fit on this axis, this b parameter will tell us how fast it was going. These should have been about the same. They probably weren't, but they were probably close. If you did everything right, you got real good points, it would have been, you know, within 20%, 25% of each other, which is about as good as we're gonna get with tracker. So what that means is that we know the initial velocity for your launcher. If you change the angle, it is not gonna change that launch speed. So we know it, we figured it out, that's now a known. If you start adjusting it, if you start turning those nuts and bolts, then the launch speed will change, because then the spring will be compressed more or less. But if you don't mess with your launcher, you can change the angle without changing the speed, and that's a super useful thing to discover. And then we know that it wasn't probably really accelerating completely down at 9.8 meters per second squared, but these are reasonable places to start with. So what that's gonna allow us to do is make a prediction for a horizontal launch, and it's gonna look something like this. I'm gonna walk you through this quickly, and then I will, or actually Ms. Adams is gonna give you another example on Thursday. Just like we were doing before with kinematics, we're gonna start by drawing a picture. So let's say we've got our launcher, and the ball is gonna go like this, and what are we gonna know in this particular kind of problem, which is not the only kind, but it's a good starting point. We're gonna know how high the ball is. We're gonna know the height of the ball. We're gonna know that the launcher is completely horizontal. We're gonna know what that launch speed is. I don't know what it is, but you do, because you measured it with tracker. So whichever launcher you used, you now should know how fast that launches the ball. And then we also know that this motion is at least approximately free fall. So there's my picture. And if you remember the steps for solving kinematics problems, the next step is we gotta pick a 0, 0. We gotta pick a 0, but now we have 2 dimensions. So typically in these kinds of problems, our 0, 0 is gonna be directly below the projectile. And then our reference axes will be up and down, left and right, with positive being up and to the right. You don't have to do it this way, but this makes the most sense, right? So now we've got our initial speed, and we've got our reference axis, we've got our height, we've got a bunch of information. How do we use this to solve a problem? On Thursday, you'll see there's one step that we still don't have to do yet, and that has to do with vector stuff. You're gonna start looking at that today, but for now, we're not gonna worry about it. We don't have to worry about that step. The next step is to make sure that we know what our variable values are. So we're gonna know our initial horizontal position is 0. Our final horizontal position, we don't know. Our initial horizontal velocity, well, it's all horizontal. So whatever that initial velocity is on your launcher, that's your initial horizontal velocity. Our final horizontal velocity, we don't know, except that we're gonna assume acceleration is 0 because it's in free fall, which actually means that its speed won't change. So it is gonna have the same speed for however long it's moving. How long is it moving? We don't know. We don't know how long this thing is moving. It's gonna move left and right until it hits the ground. In the vertical dimension, we know that it starts at whatever this height is, right, in meters, and its final position, we know that, it's 0. When this thing hits the ground, it stops moving left to right too. So our final position is when it's like resting on the ground. Its initial velocity in the vertical dimension is 0. It's not going down yet. It's gonna start going down, but it's pushed off the launcher with an entirely left to right velocity. As soon as it leaves the launcher, it starts to accelerate towards the ground, and it speeds up as it goes. But initially, it has no vertical velocity. Its final vertical velocity, we want that to be 0, but it's not. Because just like we were dealing with before with kinematics problems, we have to make sure that acceleration is constant. And the moment this object touches the ground, it stops accelerating at a constant rate. So we no longer have constant acceleration here, and that means that, that we can't use our kinematic equation. So our kinematic equations are only good until the instant before it touches the ground. That means it's still moving, but we don't know how fast it's going, but we do know its acceleration is going to be negative 9.8 meters per second squared. Okay? And then we don't know how long it's going to take. So, and again, I'm going through this quickly to give you one example. On Thursday, Ms. Adams is going to go through it more slowly with a different example, so you'll see all this again. This is your introduction to it though, and I want you to see it a couple of times. So to solve this, now the next step is we start using our equations, but we have a bunch of stuff. And one of the things that you'll learn is that sometimes it's helpful to just figure out what you can find. And if you look at the x stuff, the horizontal dimension, what you'll see with all the equations that we have is we can't really find anything. We can't figure out how far it goes if we don't know how long it's been moving. And we can't figure out how long it's been moving if we don't know how far it goes. Its speed is the same. Any equation we use is going to end up 0 equals 0, basically. And that's not super helpful. In the y dimension, though, we have equations that can tell us everything we want. We can find how fast it's going to be moving down right before it hits the ground. And we could, but we don't need to do that. What's more useful is this. We can find time. We know where this thing starts vertically. We know it's not moving initially toward the ground, but it accelerates toward the ground at this rate. That means we know exactly how long it's going to take to hit the ground. We have an equation that we can use with these variables to figure it out, and it's this one. Y equals initial position plus initial vertical velocity times time plus 1/2 times vertical acceleration times time squared. Our final position is the height. Our initial position is 0. Our initial velocity is 0. Our acceleration is negative 9.8. And what we're going to get here is that, so we can solve this because it's not a quadratic, but we're going to put it into the quadratic formula because it'll be helpful. If we put this into quadratic formula language, what we're going to get is negative 4.9 t squared plus negative h equals 0. Okay? And so if we put that into the quadratic formula, our a would be negative 4.9, our b would be 0, and our c would be negative h. Okay? Except, actually, I did this backwards, and I'm sorry about that. It's actually, it's going to be positive h, my bad. Let me just redo this for clarity. Our final height is 0. Our initial height is h. So this is going to be plus 0. So our quadratic is going to be negative 4.9 t squared plus h equals 0. Okay. So how can we use this to find time? Well, if we know how high up above the ground it is, if that's a quantity that we can measure, that we know somehow, then we can figure out time. And once we know how long this has been moving vertically, we also know how long it's been moving horizontally. We have to. It's not moving for a different amount of time in the vertical dimension from the horizontal dimension. It's moving the same amount of time in both dimensions. Once we know time over here, then we can find final position. Final position is going to be equal to initial position plus initial velocity times time plus 1/2 times the horizontal acceleration times time squared. Our final position is what we're trying to find. Our initial position is 0. Our initial velocity is some known thing, the amount of time we just found, and the acceleration is 0. So let's try this right now, only without a launcher. Let's try it with a virtual launcher. So I'm going to set this particular virtual launcher at 10 meters, perfectly horizontal launch, and I'm going to set the speed to, let's say, 4 meters per second squared. So we've got 4 meters per second. 4 meters per second is our initial speed. 10 meters is our launch height. Okay? So if we go back to here, we now know that our initial height is 10 meters, and our horizontal speed is 4 meters per second.